Hello, welcome to another one of our lessons in our chemistry lecture series. The objectives that will be covered in this topic will include explaining the principles involved in the different types of titrations. We have redox titration and we have thermometric titration. In a redox titration, the same procedure would be carried out in terms of your table, taking your volumes of your titrant, and even pipetting out the volume of your titrand or the analyte. Now, the difference is between redox and acid-base titration is that in redox, we do not use an indicator. The strong colors that comes with your oxidizing and your reducing agents, they act as their own indicator. Now, you might not understand fully the term oxidizing agents and reducing agents, but we will be doing that topic next. And that topic will explain the concept of oxidizing and reducing agents. But I will still attempt on clarifying some things. Now, here we have our burette, and our burette contains an oxidizing agent. Now, an oxidizing agent is a substance that oxidizes another substance while itself is reduced. A reducing agent is a substance that reduces another substance while itself is oxidized. So in this case, let's say we have iron 2 sulfate as our analyte, and our titrant is potassium permanganate. Now, so KMnO4 is your oxidizing agent, and iron 2 sulfate is your reducing agent. So what is happening? Every time you drop a drop of KMnO4 into the solution of iron 2 sulfate, the iron 2 sulfate, being the reducing agent, will cause the KMnO4 to be reduced from purple to colorless or pale pink. So what happened? MnO4 minus is purple. So this is responsible for the purple color in KMnO4. It moves to Mn2 plus, which is colorless. So Mn here comes with a +7 oxidation number, and it moves to Mn2 plus. So manganate 7 ion move to manganese 2 plus ion. So therefore, this was reduced. Whatever is reduced is the oxidizing agent. So KMnO4 is being reduced, so it is the oxidizing agent. Iron 2 plus is pale green, and it should move to iron 3 plus. So we see where we have an increase in oxidation number. Where there is an increase in oxidation number, we have oxidation. Whatever is oxidized is the reducing agent. When you react these two species, the oxidizing agent causes iron 2 plus to be oxidized to iron 3 plus, as well as the reducing agent iron 2 plus causes potassium permanganate to be reduced from +7 to +2. So this reaction is called a redox reaction. Now, the moment that there are no more Fe2 plus ions present, then you'll have a sharp color change, and that would signal the end point of our reaction. Remember, we do not use an indicator for redox titration. So again, if I have MnO4 minus, MnO4 minus, MnO4 minus, and here I have Fe2 plus, Fe2 plus. Every drop of MnO4 minus into 2 plus will cause a redox reaction to occur. So Fe2 plus, being a reducing agent, will cause MnO4 minus to be reduced, while MnO4 minus, being an oxidizing agent, will cause Fe2 plus to be oxidized. And so this will go from purple to colorless, while this will go from pale green to red-brown. And that is what happens every time you drop this into this. Now, the moment that all of the Fe2 plus is completely oxidized, then there is no more Fe2 plus to reduce MnO4 minus from purple to colorless, and so the solution will now change and keep its strong purple color because MnO4 minus is responsible for that strong purple color. That explains how redox reaction occur. Let's look at thermometric titration. Now, thermometric titration is a new concept to this syllabus, but it's not difficult or different from the other two types of titration that we looked at. The only difference is that we will be looking at temperature change this time. So, a thermometric titration is one where an acid-base reaction produces heat. In other words, when you react acid with base, the reaction is exothermic, which means that it produces and gives off heat. Now, during that addition of acid to base, heat is being produced, but the heat produced will be the highest at the neutralization point, or the end point of the reaction. And then the solution will start to cool. So the principle is very simple. You add acid to base, heat is given off, you take the temperature at different intervals or at different volumes of acid or base added. Then, when you reach the highest point, you continue to take the temperature when adding, because at that point, there's no more acid to react with base, and so the solution will start to cool. So, it rises and reaches a maximum point at which we find that to be our neutralization point. It then starts to cool, and you'll take the temperature for a certain time to ensure that we get a nice curve so we can find our point. Now, if your graph is done where you get lines, like for example here, this is a straight line and this is another straight line, so this will represent the maximum temperature. Now, this volume here is a volume that we would use in our calculation, similar to the volume we use in the acid-base titration from the table. So this would represent our end point. Remember that the end point is different from the equivalence point. However, at this level, we normally use it interchangeably. So this volume here will be the volume we used in the calculation. So when I run, for example, here we have acid in the burette and base in the polystyrene cup. When I run my acid from the burette and take my temperature at different volumes added, it will increase until I reach my neutralization point where the acid completely neutralizes the base, and then the temperature will start to fall.